Hello, everyone. So, this week we are going to talk about the scientific revolution. And in the period of history, last session we talked about some of the last alchemists in their complete sense. We talk about people like Paracelsus, who, being an alchemist, he believed that the goal of alchemy was to produce the so-called philosopher's stone in the sense of producing a medicine that could cure any disease. Or we had other examples like Glauber, who was also focused on this medical purpose or the medical path of alchemy, and he produced the salt mirabili that could be used for curing diseases, and at the same time he found on it like an opportunity for business, something that later on, and we will discuss today, people like Robert Boyle was very against because he thought of alchemy like a way to understand the world more than a way to produce profit, let's say. Also, we talk about some influential works like that of um, Agricola and his book called The Remetallica, on which he describes the mining activities, mining sector, and the technology available for the time, and specialize on the mining. So, how is the process of mining and the technology available at the time? So, about the scientific revolution, we can say also that at this period of history we live what is called like the Renaissance, on which this movement brought a new perception of the human being. So humans were not longer the result of a sin according to Christian Catholic philosophy, but they were thought as the creation of God. So this is a important differentiation because it impact not only in in arts but also in technological advances, because in this challenge then the human, when became the center of study, it could challenge previous knowledge, previous concepts. And in this sense Renaissance was not only a copy from the classic Greek philosophers or a restart of the ancient Roman knowledge, but it moved farther, or it moved forward based on analytical methods that the Greeks were missing. So they were mixing not only these first principles of the Greeks, but they also developed other techniques based on experimentation. Mm, we also concluded last session that these winds of change were not only in a philosophical or intellectual way, but also in a more practical way. Like now, the compass was invented, the clock, the watch, the clock was invented as well, and this served to the sailors to expand the limits of the known world. And during this period of history, the known world expanded to three times. So it was an expansion of land and knowledge what was influencing the Renaissance. About the origin of this movement of the Renaissance, it is claimed that the Fourth Crusade might have a large impact because during the end of the last or the Fourth Crusade, uh, it was occupied and sacked and looted the capital of the Byzantine Empire, Constantinople, and a lot of people, well-educated people, fled the city, mainly towards Italy, and they brought with them the ancient books from the Roman times and the Greek philosophers. You have to remember that this capital of the Byzantine Empire was the last city of Roman uh, from the ancient Roman Empire. So they brought with them all this knowledge to Italy, and with the time it was incorporated into society and brought the the process of the Renaissance. One part, one significant discovery or development that could help to start this revolution was the development of the printing press, because before that, all the knowledge was highly related to the church. As you must know that during the Middle Ages, 90% of the people was illiterate. They couldn't read. So only 10% of population was able to read and to spread and to discuss, which was written by ancient times. And it soon changed after the printing press, because now the knowledge was democratized, let's say. So it was free, or much free access. Like you have to think that one of these books, which contain, for example, the knowledge of the ancient Greeks, it could have a cost similar to a farm. So the access to information was very limited, not only because people couldn't read, but because of the price of accessing the information. With the printing press, all these things changed, and the access to knowledge was available for everyone. So these are like the supports on which the scientific revolution uh, took place. We will see now the presentation. In this period of history, we find some people that they were defying the traditional knowledge which was promoted by universities and the church. As I said 1 minute ago, the knowledge was highly controlled by the church, and they put some censorship on different ideas or concepts that they thought was against the teachings of the Bible, or sometimes the Aristotelian uh, philosophy. One of the examples for this censorship was applied against Giordano Bruno, who was an Italian Dominican monk, philosopher, poet, cosmological theorist, and Hermetic occultist. And what he proposed is that he had a revelation in a dream. He had a revelation on which he could see that if God is infinite, then is His creation, and therefore the cosmos can be infinite. And this was not accepted by Roman Catholics, Calvinists, and Lutherans, and rejected his ideas. But what is important about this claim is that he was based on some ancient knowledge, like I said before, for example, in Epicurean philosophy, that they believe in the infinite universe, and also he supported some ideas from the Hermetic tradition. Like when we talk about alchemy, we say that there was this Hermetic tradition, which was a kind of philosophy and religion that tried to explain some natural philosophy as well. And in those documents, there are some claims like the sun is the center of the universe and the other planets were orbiting around the sun. So these are ideas that were clearly not supported by the church, and therefore he was excluded and he had to travel to different cities teaching his his opinions, let's say. But he went even farther because he proposed that if the cosmos is infinite, then why not to believe that there are life in other planets as well? And this kind of claims brought him into prison, and finally he was burned in a fire by the church. Other persons that were defying the claims from this geocentric system and anthropocentric were Galileo Galilei and Copernicus, who developed a theory to explain how the center of the universe was not the Earth, but the the sun, and that they were orbiting through through space. And in the case of Copernicus, he even developed some mathematical support for these claims, the same like Galileo Galilei. But we have to remember that some of the first heliocentric or the first known heliocentric system was not from Copernicus and Galileo, but from Aristarchus of Samos, the Ionian cities we talked in previous sessions. So what we see in this period of history is that some of the ancient Greek knowledge were pushed further by the new technological advances like mathematical applications, and in some cases, it was against the traditional knowledge which was promoted by the church and universities of the time. And this opens the opportunity for the appearance of some of the most important scientific minds, like in the case of Isaac Newton. With Galileo Galilei, we also enter what is called the scientific revolution. And at the beginning of this period, or at this time of history, we can clearly see the difference between different natural sciences. For example, in one hand, we have physics and astronomy, that since ancient times it was understood the importance of mathematics and quantitative measurement. While on the other hand, in the field of chemistry, the knowledge was still left behind by these alchemical procedures and mysticism and esoteric knowledge related to alchemy. Uh, And with the scientific revolution, we also have to talk about one of the most important and influential scientists in history, which is Isaac Newton. About him, we can say that he was born in the year 1642 in North England, and this is the same year of the death of Galileo Galilei. He was born in a wealthy family, but without educational background. So it is said that Galileo was the first member of his family to be able to write his name, for example. Mm, just a few months after he was born, Newton was born, his father passed away, and later his mother got married with Reverend Smith, who did not accept Newton like a baby. So Newton had to stay in his family farm, living with his grandparents until he was 10 years old when his mother came back with three new brothers. Mm, in 1661, Newton was admitted to Cambridge, and at this time he was taught about the teachings of Plato and Aristotelian philosophy, and a little bit about the philosophy from Descartes and all the scientific method developed by Descartes. About his character, it is said that he was problematic and quite close person with few or none friends. And there is a sentence that is attributed to him that he said that Plato is my friend, Aristotle is my friend, but my greatest friend is truth. Also showing about his character that he was quite a lonely person, and but this attitude and this character also helped him to be close in himself and develop his theories. In 1665, the pest hit Europe hardly, and Cambridge students were sent home. So it's precisely this period at this time when start what is called like the Annus Mirabilis for for Isaac Newton. And in this period, he found or developed what we know like calculus, which was a new branch of mathematics, the theory of colors, which was a new branch for physics in optics, and his theory or his gravitational theory and laws of motion, which we know today like dynamics, which is also an important field in physics. So, with 23 years old, Isaac Newton, during this 1 year of quarantine, he was able to develop at least these three brand new fields of science, which is quite impressive. Uh, the problem was that Isaac Newton, because of his own character and personality, he was quite close about these discoveries and didn't show it to others. So he kept it for himself. After his return to Cambridge, he was assigned to teach, and later he developed other advances in or technological advances, mainly the refracting telescope. And his developments were published in the Royal Society, but soon he met opposition by Robert Hooke, who at the time was a well-renowned scientist. And then because of this conflict between Newton and Robert Hooke at this time of history, uh, Newton decides not to publish again his work. So he presented some of his results at this time, but because of the opposition of other scientists and some of them with a big name like Robert Hooke, then Isaac Newton retrained from publishing his works, and he closed himself even during 10 years period in the field of alchemy, which is a paradox because in one side we can see that he was pushing further science and quantitative measurements and application of mathematics, but on the other side, in our scope of or our field of study, which is chemistry, he was still lagged with the alchemy practices and all these mm, type of developments, let's say. And more specifically, when Newton tries alchemy, he goes through the mineralogical pathway. So he's trying to reach transmutation, and even not so long time ago, it was taken some samples from his hair, Isaac Newton's hair, and high levels of mercury was found. So like mm, like a clue of his past on his work on chemistry, like an evidence. Mm, After all these 10 years of Newton focusing on alchemy, it was a natural coincidence that the Halley's comet was visiting our planet, and Newton was pushed by Edmund Halley to try to describe the orbit of the planet, and which is also working for other, not only for the comet but for other planets. And because at the time other scientists were already trying to describe these orbits, these elliptical movements, but the theory was not still developed. So Edmund Halley went to Cambridge to visit him and ask him to develop a theory to explain this phenomena. But Newton already had the background for explaining this work with his developments on calculus and the theory of gravitation. So soon after they met, Newton was able to publish his results with the theory of gravitation. And in 1686, he published also the one of the most influential documents in history and of science, which is called Principia Mathematica. And later in 1704, Newton publishes Optica, which is about his theory of color and optics, of course. Isaac Newton dies in 1726, and at time of his death, he was a wealthy man because he was working also for the crown in England, and he was already the most famous scientist of his time. Other conflicts that confronted or that were exposed to him during his lifetime was about the discovery or development of calculus, because even though uh, Newton developed this branch of mathematics in 66 around, uh, he was not the first to publish his work, but the first to publish on this new branch of mathematics was a German mathematician called Leibniz. And then there was this dispute over who was the pioneer to develop this new application. However, because of the great fame that Newton won during his lifetime, and when he was the leader of the Royal Society, let's say that he was attributed to this development to be the first one to achieve this application of mathematics. So Isaac Newton showed to us very clearly this dispute or this large difference between natural sciences like astronomy and physics and alchemy, because in chemistry he was still working with alchemy and all these obsolete knowledge, while in physics and astronomy he was already developing some of the most important applications that we still even today, at some extent at least. And here is important to notice that even though from ancient times it was known that there are vapors and air-like substances, and even air was one of the four elements in the theory developed by the Greeks, even though this was a common knowledge that people could feel and experience in their daily lives, the gases itself, it was not the main purpose of work by alchemists. So if you check what we discussed before about alchemy, we always came to see that alchemists were focusing in development of procedures to obtain or to treat solid or liquid samples, in part because it's much easier to handle this type of substances than air itself. So even alchemists did some work to contain some airs or spirits, how they call it, for example, in the case of alcohols. It was only much later with John Baptista van Helmont that gases offer the opportunity to do the first attempts of quantitative measurements in the field of chemistry. So Baptista van Helmont, what he did was to made a control experiment for the growth of a tree or a plant in a contained environment. So he was carefully measuring how much water was added and how much soil was available to the growth of a tree. And he was pursuing to find the reason of life in this type of experiment. So he was doing some experimentation with biological and chemical purposes. And during this experiment, he also did burning of wood and trying to understand this air-like substance which was produced. And he came to the conclusion that even though it was similar in some aspects to air, it was not completely the same. So he was able to differentiate that there was another type of air or gas that he called like gas sylvestre. And of course, this gas is what we define today like carbon dioxide. So with him, gases became less mysterious, let's say. And he was the person who gave the name gas to these air-like substances. What he did was a spelling or a Flemish spelling because he was Flemish origin. So the word gas is a Flemish uh, script for the word chaos, which in ancient Greek philosophy was the material which is the origin for the universe. And then it's interesting to see how the gases that were mm, less mm, studied during the alchemy and for the alchemists, it was now the substance which opened the door for these chemists to start with the quantitative measurements. At the same time, other properties were discovered for gases and some technological advances as well, like, for example, the development of barometer for measuring pressure. And it was Evangelista Torricelli who, who found that air was able to exert pressure and that air could support a column of mercury of 30 inches, for example. And other technological advances were, for example, the development of air pumps by Otto von Guericke, among others. Then, moving forward with the work on gases, it was Robert Boyle who discovered an inverse relationship between volume and pressure. So it's a clear advance in relation to the barometer developed by Torricelli. And for this, he was doing countless experiments with the air pump developed by Otto von Guericke. And about his life, we can say that he was one of the sons of the seventh son of one of the richest men in Britain, and he centered his life to the development of chemistry. For that purpose, he wrote some books. Among them, the most prominent is the so-called The Skeptical Alchemist, on which he clearly wanted to push further the chemistry, but also shows the two faces of him as a scientist. In one side, he was still focused on alchemical transmutation of base metals for the manufacture of gold. And on the other hand, he developed the basis for the new definitions of elements and, and quantitative measurements. In his book, he is always referring to what he calls like the vulgar chemist. And this is a reference for those chemists who were working mainly in the pharmaceutical purpose. And for him, this was a vulgar work because it was mainly focused on the development of a market for money. But he believed that chemistry was an instrument for understanding the world. Mm, about his definition of element, we must say that at his time still was alive all the theory of the four elements developed by the Greeks, as we saw in a previous session. But for him, the definition of element was something more provisional. So he started from an experimental point of view where all the substances must be tested. And if this a given substance can be broken into simpler substances, then it was not an element anymore. So like this, he gave a provisional mm, significance for elements, and it's a completely different definition than we see today. Even more, he was uh, he believed that the base metals known by the ancients were not elements itself, because he believed that it was just a matter of time and method to break these substances into simpler constituents, which is clearly wrong because today we know that the seven metals known by the ancients are elements itself, like, for example, gold, tin, iron, and so on. When he said this part of skeptical, it was a clear reference to his vision that it the knowledge should be obtained by experimentation, and then he was skeptical on the ancient conclusion by the Greek philosophers from first principles. As you should remember, the Greeks, the philosophers, they came to their theories and conclusions based on what is called first principles, so on the reasoning. So it was a intellectual experiment, let's say, but not a physical or chemical experimentation. And therefore, Boyle was skeptical about this type of conclusions. Mm, Other important thing about Boyle is that himself he was considered an atomist, and because of this, some of his work was seen by the contemporaries like a simple continuation of Van Helmont theories and works, what we described in the previous slide. About Van Helmont, I forgot to say that he believed that all substances were composed from one single element, so not four like the Aristotelian, but more like Miletus. So he believed that water was the primordial substance of which material could be produced. Maybe because he was oriented in this biological and chemical knowledge, where water was a primordial mm, substance for the development of life, for example. So Boyle believed the same, except that he didn't talk about water, but what he called Catholic matter. So you can see also things about his character and the history of society at the time, where knowledge was profoundly related to the church. So even during the Middle Ages, which was before Boyle, uh, almost 90% of the population was illiterate, and only that 10% was mainly people related to the church, priest or any other job related to the church. Continuing with Boyle, we can say that in his development of the inverse relationship between volume and pressure, he didn't mention the effect of temperature. Some people say that he didn't do because he believed it was obvious that temperature should be kept constant for this relationship to be true. But in continental Europe, there was another scientist called Edme Marriott who clearly state that for this to be true, the temperature must be kept constant. Therefore, in continental Europe, sometimes the relationship is called Marriott's law, or sometimes they use both names to describe this phenomenon. About Boyle, we also have to say that being an influential person, he promoted or urged the British government to repeal the law against alchemical manufacture of gold. So it also shows that even though he was an example of the first attempts to do quantitative measurement, he himself still believed in these possibilities for transmutation. He believed that this law against alchemical manufacture of gold, it was against the development of science, and that's why he asked to demolish this law. And the study of gases didn't have only theoretical implications, but also practical ones. So before the work of gases and the development of air pumps and steam engines, society relied completely on the power of humans, the muscles of humans and animals to develop industrial processes. So, for example, it is known that an adult man can produce only between 70 and 150 watts of power, and that around 10 men are needed to equal the power of a horse, for example. And with the development of these new technologies with steam and steam engines, we can see that, for example, in England and Wales, the energy consumption started to increase significantly since 1650 to 1850. So multiplying almost by more than 10 the energy consumption in these regions. And from the theoretical point of view, the work developed by Boyle, it was also the first evidence that, or experimental evidence that supported the theory of atomism, because if matter could be compressed, like in the case of gases, and then it means that between atoms there must be an empty space. And if there is something empty space, then matter is not constituted by a continuum, like it was believed according to Aristotelian philosophy, but by particles that they are free to move and there is a space between them. So this was an important experimental evidence for the existence of atoms. So this gas, which was a substance or which was difficult to manage and avoided for alchemists, now it proved to have practical implications and also theoretical ones. At this point, we should talk then about the steam engine, which is the main factor for the Industrial Revolution. So the first model was built by Denis Papin in 1690, but it was Thomas Savery who developed a first functional system of 1 horsepower or 750 watts. It is important to recall that at this time there was no enough experience for handling steam at high pressures, so the technology was quite dangerous. After Savery, Thomas Newcomen developed in 1712 a system, an engine of 3.75 kilowatts, and which is a significant achievement. And it was used mainly for pumps in mining, but it was impractical because of if there was no fuel supply close. And later, it was James Watt who, in 1769, patented and improved previous designs and made it practical at the end of the 18th century. He was successful with this design and it could install approximately 500 engines with an average of 20 kilowatts, and the largest unit was already 100 kilowatts. And it is at this point where, for the first time, humans no longer depended on their own muscles or on animals to produce chemical or physical changes. And the source of power at any time and any place, it was only needed boiling water to produce this energy. Due to the popularization of the steam engines as developed by Watt, Newcomen, and colleagues, a high requirement for fuel started to appear in large European cities. Mm, just to give an example of how this could impact the landscape in European cities, I show to you in this slide a simple calculation to estimate the area required for plantations versus the area which was urbanized. So we know from photosynthesis that 0.5% of incoming solar radiation converts to phytomass. Also, it's known that the best annual fuel wood productivities of traditional fast growing species like eucalyptus is no larger than 10 tons per hectare. And we also know that the energy density of dry wood is around 18 gigajoules per ton. Based on these numbers, we can calculate the number of watts which are produced per hectare per year, as shown in the equation to the left. And this gives us a value of around 5,700 watts per hectare per year, which is equivalent to a supply of 0.6 watts per square meter. It is also known that a large 18th century city will have required at least 20 to 30 watts per square meter of its built up area for activities like heating, cooking, or artisanal manufacturers. Uh, if you make a calculation based on the previous results, you can estimate that an area of around 40 times larger is required for wood production in order to be able to supply the required power. Uh, However, this number is conservative because the fuel which was consumed for the engine was not wood necessarily, but charcoal. And the process to produce charcoal is highly inefficient, where the ratio charcoal to wood is around 1 to 5. It means that if we correct this number by that ratio, it will give us a value around close to 200, so around 200 times larger area for plantation than for cities. However, charcoal energy density is higher, is 29 gigajoules per ton in comparison with the 18 for wood. So you have to correct again, and this will give us an area requirement between 40 and 100 times the size of the built up areas. This has also consequences that we can experience today. And we know, for example, that during the industrialization process of countries like Belgium, almost completely they almost completely consume the natural forest in their territories. And as we experience today, started the problems with the CO2 accumulation in the atmosphere that we will discuss in future sessions. It's in this context when societies were looking for fuels and how to improve and understand the process of combustion that appears what is called like the phlogiston theory. And this is a theory that tried to answer a deeper question, which is why do some things burn? If we remember from our previous sessions, the Greeks proposed that a substance burns because it contains the element of fire within itself. This is in agreement with what we saw about the fourth element theories. However, later we saw that in the alchemy, during the development of alchemy in Arabic world, we saw that these alchemists proposed that the property of combustion was due to the principle of sulfur. So solids were composed of sulfur when they were easy to burn, let's say. But this sulfur is not necessarily the same sulfur we define today, just is a principle of that material. It was only later when Johann Joachim Becker, in his publication Physica Subterranea, that a new concept appeared, and he proposed that solids are composed of three types of earths: terra lapidea, terra fluida, and terra pinguis. This terra pinguis was the element that imparted oily, sulfurous, or combustible properties. So what we see is that even in the middle of the 1600s, there's still this strong association with the four element theory of the Greek philosophers. and it was already mixed with the notations from the Arabic alchemist. Uh, this concept or these ideas developed by Becker were not completely mm, clear, and sometimes they were erratic. But it was George Ernest Stahl who developed the theory known as the phlogiston theory. And phlogiston comes from a Greek word meaning to set on fire. According to this theory, combustible materials are rich in phlogiston, and the process of burning involved the loss of phlogiston to the air. And what was left was a material without phlogiston, and therefore it could not be burned again. This is a theory or a concept that could explain process like burning woods, for example, or charcoal. That according to the theory, materials like wood or charcoal, they are substances which have large large concentrations of phlogiston, and therefore they can be used as fuels. They can burn easily. But once the process was completed, you obtain ash, which is a phlogiston poor material, and therefore you cannot make a fire out of ash alone. Interestingly, Stahl also proposed that this phlogiston theory could be used for the process of rusting, or rusting metals or oxidation of metals. And he said that metals are substances which are phlogiston rich, and during the oxidation process they start to lose slowly this phlogiston to the air. It was interesting about the phlogiston theory, and the reason why it was accepted at his time is because it could explain things neatly, like the problem of combustion of wood, but also the oxidation of metals. Like for that purpose, what he proposes that uh, to produce a metal, you start with a rocky ore, with a rock containing the mineral in it. And what he said is that when you smelt, when you heat the mineral, the rock, what you are doing is transferring the phlogiston from the fuel, like in this case could be, for example, charcoal, to the rock. And in the rock, it is used to produce the metal. So at the end of the smelting process, what you get is a metal which is phlogiston rich. And the fuel which was consumed, it remained like a phlogiston poor substance in the form of ash. Once this smelting and the process, once the smelting process has finished and this metal has been produced, then this metal starts process of oxidation when it is let to the atmosphere. And what he says is that because metals are phlogiston rich, they start to lose this phlogiston to the air and produces like the oxides, so the calx, what they called. And, and this could be explained by this phlogiston theory. However, we know that there are some contradictions or experimental contradictions on this theory. And for us, it seems like a serious problem today. But as I said in this presentation, chemistry in this time, it was not so strongly attached to mathematical principles and quantitative measurements, so they let it pass. That's something that it wouldn't happen today, for example. The first to find this contradiction was a scientist called Hermann Boerhaave, and for him it was impossible that rusting and combustion are somehow similar processes. For him, it couldn't be the case, and he said that the main difference was because of the flame. So during combustion, you need the flame, you need to see the flame, but for rusting, you don't see that flame. And Stahl argued that the reason for this is that even though they are the same process, the speed at which the process is taking place is completely different. So combustion is a much faster process, and this fast release of phlogiston produces the light and the fire we see, while rusting is much slower process, and therefore you don't see the flame or the fire coming into place. This for one part, but the other problem was that if phlogiston is a substance, then it can explain the process of combustion. So if the phlogiston is released in the wood, it is perfectly okay because the ash is less, it has less mass than the original piece of wood. So there is a mass loss which can be explained by the phlogiston. So let's say that the ash plus the phlogiston would make the piece of wood that it was combusted. But in the case of rusting, this is contradictory because once a metal is rusted or oxidized, it gains mass. So it's not losing mass like in the case of combustion, but it is gaining mass. And then it opened the question if there was only one type of phlogiston or two. And because then in the first case, in the case of combustion, it seems like the phlogiston had a positive mass. But in the case of rusting, it seems like the phlogiston had a negative mass because the mass is increasing. So how is it possible that if a metal is losing phlogiston, the mass is increased? This is not possible. This wouldn't be possible unless the phlogiston has a negative mass. So this was a serious question for us. This will be a serious question for us today, but in the 18th century, they didn't pay much attention on accurate measurements, and the theory took place and it was spread through the scientists in Europe. So this is the end for the session today, and thank you so much for your attention.